Ever wonder why a guitar solo can give you goosebumps? Or why an ambulance siren suddenly changes pitch as it zooms past you? No, it's not magic, it's physics. And today, I'm about to show you how sound can bend, bounce, and even time travel. Well, almost. We're diving into the science behind musical instruments, how string sings, and the mind-blowing Doppler effect that makes sound chase you down the street. By the end, you'll not hear sound music and sirens differently. You'll understand them on a whole new level. So get ready, because this isn't just sound. It's sound in motion, sound amplified, and sound that tells a story. And for our objectives, we have explain the Doppler effect and describe how motion affects the frequency and pitch of sound waves in real-world scenarios. Second, describe the physical principles that govern sound production in string instruments, focusing on how length, tension, and mass of strings affect pitch. And lastly, apply scientific reasoning to compare how sound behave under motion, or the Doppler effect, and through stationary mediums, or the vibrating strings in musical instruments. Just a quick fun fact. The idea was first proposed back in 1842 by Christian Johann Doppler. So this is a classic physics concept that's still helping us understand the universe today. So now, let's talk about something super cool that you've probably heard before, even if you didn't know there was science behind it. The Doppler effect, also called Doppler shift, is a phenomenon that happens when there's motion between the source of a wave and the person observing it. So let me break it down with a real-life example. Imagine you're standing on a sidewalk and an ambulance drives by with its siren on. As it approaches, the siren sounds higher in pitch. As it passes and drives away, the siren suddenly drops to a lower pitch. That change in pitch is because of the Doppler effect. So what's actually happening? When the source of the sound moves towards you, the sound waves get compressed and the frequency increases, so the pitch sounds higher. When the source moves away, the waves stretch out, lowering the frequency, so the pitch sounds lower. And here's the cool part. It's not just sound. The Doppler effect also happens with light, with it's super important in astronomy. When a star or galaxy is moving away from us, its light shifts towards the red end of the spectrum and is called a redshift. If it's moving towards us, we get a blue shift. This effect is one of the tools scientists use to figure out if stars or galaxies are moving, and even how fast. Here we have our formula. It is f prime is equals to f times v plus or minus v sub o over v plus or minus v sub s, where f prime is the observed frequency, f is the actual frequency of the source, v is the speed of the wave in the medium, v sub o is the speed of the observed relative to the medium, or the positive if moving towards the source, v sub s is the speed of the source relative to the medium. It is positive if moving away from the observer. There is only one Doppler effect equation, but it varies based on the velocities of the observer and the source of sound. Below, we will explore how the Doppler effect equation applies in different scenarios. There is only one Doppler effect equation, but it varies based on the velocities of the observer and the source of sound. Below, we will explore how the Doppler effect equation applies in different scenarios. Source moving towards a stationary observer. In this case, the observer's velocity is 0, or the v sub o is equals to 0. By substituting this value into the Doppler effect equation, we derive the equation for a source moving towards a stationary observer. Then we will have this formula. B. Source moving away from a stationary observer. Again, since the observer's velocity is 0, we can eliminate b sub 0 from the equation. This time, the source is moving away from the observer, which means its velocity is negative to indicate the direction. Thus, the equation now takes on a different form. The formula now is C. Observer moving towards a stationary source. In this scenario, the speed of the source, or the v sub s, is equal to 0, allowing us to simplify the equation accordingly. Then the formula will be observer moving away from a stationary source. Here, the observer is moving away, resulting in negative velocity for the observer. Consequently, instead of adding v sub 0, we subtract it from the equation since v sub 0 is negative. Then the formula will be. And this clarification should help in understanding how the Doppler effect equation changes based on different movement scenarios.
For the application, we have an example for radar and speed detection. Let's say you're driving, and up ahead, you see a police officer pointing a radar gun in your direction. That small device can instantly tell how fast your car is going. So, that is Doppler effect. The Doppler effect explains what happens when a wave source and an observer move relative to each other. You've probably noticed it before, like when an ambulance passes by and the sound of the siren changes as it goes past. That shift in pitch is the Doppler effect in action. In radar systems, the same principles applies, but instead of sound waves, we're using radio waves. A radar gun sends out radio waves toward a moving car. These waves hit the car and bounce back to the device. Now, here's where the Doppler effect comes in. If the car is moving toward the radar gun, the reflected waves come back at a higher frequency. If the car is moving away, they return at a lower frequency. This change in frequency is measured by the radar system. Using that frequency shift and some math, it calculates how exactly fast the car is going. This method is accurate, fast, and doesn't require any physical contact. That's why it's widely used in traffic monitoring. The Doppler effect actually helps control speed limits, reduce accidents, and improve road safety in the real world.
And now, I'm presenting on Doppler weather radar and how it helps detect tornadoes. So a real-life example is the 2011 Joplin tornado. Doppler radar detected strong storm rotation and flying debris using the Doppler effect, which helped give early warnings and saved lives. So here's how it works. The first one is the hoop echo. A spiral shape on radar image shows rotation, which can mean a tornado is forming or already formed. The second one is the velocity complex. When inbound and outbound winds appear close together, it shows strong rotation, a key tornado signal. And the last one is the tornado debris signature, or what we call TDS. So a radar picks up debris like parts of buildings, confirming a tornado is on the ground causing damage. So in short, Doppler radar uses physics to spot tornadoes early and help protect people.
Now, let's proceed to problem solving number 1. Let's read it first. A police siren emits a wave with a frequency of 320 Hz. The speed of sound is 370 meters per second. The siren moves away from a listener with a speed of 50 meters per second, and the listener is moving away from the siren with a speed of 20 meters per second. What frequency does the listener hear? Now, we have the given F here. What is the F? The F is the source frequency, so our given is 320 Hz. While the V is the speed of the sound, so our given is 370 meters per second. The VO, or the observer's velocity, we have 20 meters per second, while the VS, or the source velocity, it's 50 meters per second. Now, the missing value is the F prime, or the observed frequency. So this is the frequency the listener hears. To get the value of the observed frequency, we have speed of sound minus observer's velocity multiplied by source frequency over speed of sound added to the source velocity. Using this formula, we will get the difference between 370 and 20 multiplied by the source frequency, which is 320, divided by the sum of 370 and 50. Now, F prime is equals to 350 multiplied by 320 over 420. So plugging it into our calculator, we will get the answer of 266.66 or approximately 266.67. So this value, 266.67, will be our observed frequency. Now, we get the F prime.
For problem 2, we're dealing with the Doppler effect, specifically how the frequency of a siren changes depending on whether the fire truck is moving towards or away from a stationary observer. A fire truck emits a siren at a frequency of 870 Hz. We are to find the frequency heard by a stationary observer when A. The truck is moving towards them at 28 meters per second, and B. When it's moving away from them at the same speed. We're given that the speed of sound in air is 343 meters per second, and the observer is stationary, so their speed is 0. We'll use the Doppler effect formula, which is F prime is equals to F, quantity of B plus minus V sub 0 over quantity of V plus minus V sub S, where F is the actual frequency equal to 870 Hz, V is the speed of sound equals to 343 meters per second, V sub 0 is the observer's speed, which is equals to 0, V sub S is the source speed equals to 28 meters per second. Part A. When the fire truck is moving towards the observer. Since the truck is approaching, the sound waves are compressed, so the frequency increases. We plug into the formula F prime is equals to 870 times the quantity of 343 over 343 minus 28. 870 times quantity of 343 over 315 is approximately equal to 947.33 Hz. So, the observer hears a higher pitch, about 947 Hz. B. When the fire truck is moving away from the observer, now the waves are stretched out, making the frequency lower. So we plug this into the formula F prime is equals to 870 times the quantity of 343 over the quantity of 343 plus 28 equals to 870 times the quantity of 343 over 371, which is approximately equal to 804.34 Hz.
Let's now move on to musical instruments and the laws of strings. We all know that musical instruments are objects or tools we use to produce sound or music. There are different types of instruments, such as string, percussion, and wind instruments. For now, let's focus on string instruments. String instruments produce sound through vibrating strings. Examples are guitar, violin, and harp. When we pluck or strike a string, it vibrates, and that vibration produces sound. According to our presentation, string instruments operate based on the principles of wave motion and resonance. But what do these terms mean? Wave motion refers to the transfer or spreading of energy caused by vibration. When a guitar string vibrates, it moves the air around it, creating sound waves. And these sound waves, these are the sounds we hear. But what about the resonance? What is resonance? When we strum a guitar, the vibrating string is connected to the body or the sound box of the guitar. That vibration causes the body of the guitar to vibrate as well, amplifying the sound. In simple terms, resonance is the response of the guitar's body to the vibration of the string, which helps produce a louder and fuller sound. String instruments like guitar, violin, and even the piano work using wave motion and resonance. When you pluck a string or strike a piano key, which causes a string to vibrate, that vibration creates sound waves in the air, which is the sound we hear. Now, what affects the pitch or tone of a vibrating string? There are three main factors. The first is the length of the string. The shorter strings produce, the higher pitch sounds, or the sharper sounds produce. Longer strings produce lower pitch or deeper sounds. Next, the tension of the string or the tightness. Tighter strings vibrate faster, resulting in a high pitch. Looser strings vibrate slower, resulting in a lower pitch. And last, the mass per unit or the thickness or weight of the string. Thinner or lighter strings produce higher pitch sounds, while thicker or heavier strings produce lower pitch sounds. So when you tune a guitar, tightening the strings raises the pitch. To get a deeper sound, you can loosen the string or use a thicker one. So how do string instruments work? The first is the frequency and pitch. The pitch of a note depends on how fast the string vibrates or its frequency. So the three main factors that control this is the length, the tension, and the mass, which I've already discussed earlier. So now we have the Mersenn's law. The fundamental frequency of a stretched string is inversely proportional to the length of the string. So having the length doubles the frequency. Next, quadrupling the tension doubles the frequency, and reducing mass per unit length to 1/4 doubles the frequency.
Let's dive into what actually happens when you pluck a string on a guitar or bow on a violin string. When a string vibrates, it doesn't just move randomly, it forms what we call standing waves. These waves have fixed points called nodes that don't move, and antinodes where the strings vibrate the most. Now, here's the cool part. The vibration creates a fundamental frequency, which is the bass and sound you hear. But it also creates harmonics, which are like extra layers of the sound that happens at higher frequencies, or multiples of that fundamental. These harmonics are what give instruments their unique voice or timbre. That's why a violin and a flute playing the same notes still sound different. Different instruments will have different harmonic profiles. Some harmonics will be louder or more dominant than others. That's what makes their sound stand out. Let's look at how those harmonics actually appear physically on a string or in a pipe. Here's a chart showing different modes of vibration or harmonics for strings, closed pipes, and open pipes. The first harmonic, also called the fundamental, is the simplest wave, just one hum. As you go up to the second harmonic, third harmonic, and so on, you see more and more segments. These segments each represent one half length. For strings, you always get both ends fixed, so it's symmetric. Closed pipes have one end closed, so that the vibration reflects differently. Open pipes have both ends open and they behave more like strings in terms of symmetry. Each mode represents a higher frequency and different harmonic. These patterns determine what we actually hear and how rich or bright a note sounds. So the string is vibrating. Great. But if that's all that was happening, we wouldn't hear much. This is where resonance and amplification comes into play. The string alone is super quiet, like a whisper. Quiet. The real sound comes from the resonating body of the instrument. On a guitar, that's the wooden top. On a violin, it's the whole sound box. These parts vibrate along with the string, amplifying the sound. They resonate at the same frequency, which makes the sound louder and fuller. Finally, those vibrations travel into the air, and that's how they get to our ears as sound waves. So the next time you play or listen to an instrument, remember, you're not just hearing a string, you're hearing physics in action.
So now I'll be talking about the physics of how a guitar works. First, when a player presses on the frets, they change the length of the string. Shorter strings vibrate faster, which means a higher pitch. Next, the tension of the string also affects pitch. Turning the tuning pegs increases or decreases the tension. Tighter strings vibrate faster and raise the pitch. The thickness of the string matters too. Thinner strings vibrate faster than thicker ones. Finally, the guitar's hollow wooden body acts as a resonator. It amplifies the sound made by the vibrating strings. Without it, the sound would be much quieter. So in short, pitch is controlled by string length, tension, and thickness, and the sound is amplified by resonance.
For the violin, pitch is altered by sliding fingers on the fingerboard. Bowing maintains vibration while the body amplifies it. How does it work? For the changing length, instead of frets, violinists use their fingers to press down on the fingerboard, changing the string's effective vibrating length. Sliding the fingers allows for smooth pitch transitions. Next is maintaining vibration. A bow is thrown across the strings, causing them to vibrate through friction. Unlike plucking, bowing sustains the vibration for a longer time. For resonance and amplification, the bridge transfers string vibrations to the hollow wooden body of the violin. This body amplifies the sound and gives the violin its characteristic tone.
So the piano works by striking. When you press a key, a hammer hits a string making it vibrate. Each piano string has a fixed length and mass, and the sound it produces is preset, not altered by the player like in a violin or guitar. So the vibrations from the strings are transferred to a large soundboard, usually made of spruce. So this soundboard acts like a giant speaker, projecting and amplifying the sound, so it fills an entire room. In conclusion, the beautiful sounds of these instruments come from the scientific interplay of physics and design. By controlling string length, tension, and mass, and using resonance, musicians bring music to life. Understanding the physics behind these sounds helps us appreciate the art of music even more.
Here are the members of GL. Lastly, thank you for listening. We really hope that you learned something today.